Continuing on with our lecture, we want to continue looking at some applications of Newton's second law, and then we'll move on and look at Newton's third law. There's a classic physics demonstration where you have a glass tube that is sealed off and it contains a feather and a coin, and you flip the tube upside down and you let the coin and the feather fall. And what you find is that the coin falls straight down, but the feather kind of falls more slowly. And that seems to violate our rule that everything falls at the same rate, little g. So how is it that the feather falls at a different rate than the coin? Well, the feather is very light and it has a very big surface area compared to how much it weighs. And so the effects of air resistance are strong enough to impede its motion. Whereas the coin, it also experiences air resistance, but it experiences a much smaller amount of air resistance relative to its weight, and so it doesn't really notice the air resistance that much. And so the coin falls straight down where the feather sort of flits away. But then what you do is you hook a vacuum pump up to the glass tube and you suck the air out, and then you repeat the experiment. And when that happens, the coin and the feather both fall at little g because there's not any more air in the tube to impede the motion of the feather. So the question then becomes, how can you handle the situation where air resistance can't be ignored? And the answer is we simply apply Newton's second law. Now remember, Newton's second law tells us the acceleration is the total force divided by the mass. So if I've got somebody falling, and here's a dude with a parachute, and so what are the forces acting on the guy as he falls? Well, there's his weight pulling him down to the ground, the force of gravity, his weight pulling him down to the ground, and then there's the air resistance in the opposite direction. Now normally, forces that point up we call positive, and forces that point down we call negative, but in this case, because the person is actually moving downward, we can choose to call any force pointing downward as positive and any force pointing upward as negative. That's why it's the weight force minus the air resistance force when you add them up. Because we know that if we have forces in opposite directions, one of them has to be positive and the other one has to be negative. And usually, whichever way something is accelerating, that's the way we line up our positive. So when you look at our formula here, we can say that the total forces are going to be the weight minus the resistance of air. So W minus R, that's the total force divided by the mass. And again, the W is the weight, and the R stands for the force of air resistance. And so that's what we have in this formula up here. So if I want to calculate the acceleration of a falling object where you have to include the effects of air resistance, you simply do it this way. So let's look at an example. Our example says a 70 kilogram man falls and experiences a 200 Newton amount of air resistance. So the question is, part A, what is his weight? And part B is, what is his acceleration? So here we have a 70 kilogram man, and his weight's going to be the same regardless of what the air resistance is. So to calculate the weight, we simply apply Newton's second law. The weight is the force of gravity, and we know that that's going to be equal to the mass, the 70 kilogram mass, times the acceleration of gravity. That's why I've written A with little g to remind me that that acceleration is gravity. But we actually have another symbol for the acceleration due to gravity, little g, which we know is about 10, 9.8 actually, but 10 is good enough for government work, so that's what we'll use. And so now I simply plug in the values for the formula. 70 kilograms is the mass, 10 meters per second squared is little g, the acceleration due to gravity. And when I multiply all that together, I get 700 kilograms times meters per second squared, and those units all multiply together to give us newtons. And so the person weighs 700 newtons. Now for part B, the question asks, what's the acceleration? Now, if the person were just falling with no air resistance at all, we wouldn't have to calculate anything. We would know that it would be 10 meters per second squared because everything falls at 10 meters per second squared. But if air resistance is reducing the acceleration, we have to take it into account, and we can use that formula we saw in the last slide. So we just calculated the weight as 700 newtons. We're given in the problem that the air resistance R is 200 newtons and the mass is 70 kilograms. So if we subtract 200 from 700, that gives us 500 newtons. Divide that by 70 kilograms, and we end up with an acceleration of 7.14 meters per second squared. Now, in the previous example, we were given a constant 200 Newton air resistance force. But actually, when things are falling and speeding up, as things go faster and faster, the air resistance actually gets bigger and bigger. Eventually, what will happen is the guy is falling or the girl is falling, they're going faster and faster and faster, the air resistance is getting bigger and bigger. Now, you've probably all experienced this if you've ever stuck your hand out of a car window in a moving car. You feel the air rushing past your hand, and you can feel that air resistance, and you know that if the car is moving faster, you feel more force of air resistance because the air is moving faster past you. So it's the same idea. If you jump out of a plane, as you fall, the air is going to be rushing past you, creating air resistance. And as you accelerate towards the ground, going faster and faster, the air resistance is going to get bigger and bigger. But eventually what's going to happen is the air resistance will equal your weight. And so I've drawn it in the picture here. You've got the weight of the person and the air resistance in the opposite direction. As the air resistance gets bigger and bigger, eventually it will equal the weight. And then what's the net force on the falling skydiver? It's zero, because once the air resistance and the weight equal the same amount, they cancel one another. And guess what? At that point, you stop accelerating because there's no longer an unbalanced force. And so your velocity stops increasing. So here's what happens to recap. You jump out of the airplane, you fall faster and faster and faster because gravity is accelerating you downward. But the air resistance is getting bigger and bigger, so when the force of air resistance equals the force of gravity, you stop accelerating. Now that doesn't mean you stop moving, of course, but it means you stop increasing your velocity. And so at that point, your velocity is constant. And we call that the terminal velocity. And the terminal velocity occurs when the force of air resistance equals the force of gravity, and then you will be at a constant velocity called the terminal velocity. And that's the fastest velocity that you will move at as a falling object. And we can actually see that this principle applies to parachutes. What is the purpose of a parachute? A parachute basically cups more air to create more air resistance. And so a person falling with a parachute is experiencing a much bigger air resistance. And so that bigger air resistance will match their weight much more quickly, much sooner. And so the person won't have as much time to go faster and faster and faster, and so it will slow them down. And so that's the main purpose of the parachute, is it increases the resistance to reduce your terminal velocity. And so when you land on the ground, you don't get splattered on the ground, you can actually just land on it.